So this type of the problem, one problem we take, and it is better to do this kind of the problem. Right? So this is the 2016 one problem came regarding the inverted U-tube manometer. You'll see here oil is there. On pipeline there is oil. Density of the oil is given here 800. So density of the oil is given 800 at P. Another point is the B point. You are asked to finding out the pressure difference between PA minus PB. That is your question. And you see here as a manometric fluid, they are using as air. So air density is much more less than the oil density and water density. So density of air is much less than water density and oil density. So that is the beauty of taking the inverted type. So as the density of the air is less, so it will goes upside. So that is the way. So how to get this kind of the problem? How to solve this kind of the problem? Here, what is the reference point? First of all, reference line you have to choose. So reference line you can able to see here. You see here, that is the point beyond which there is a air. And the similar horizontal point at here, beyond which there is a air. So this line you can choose as the reference line. This is the reference line you could be able to choose. Because beyond this air, both sides there is a air. And in this point and in this point, there is a same pressure will be happening. Because how much it will go in this side, the same direction it will come down. So the same pressure will be reached. Here, whatever the pressure, the same pressure will be at this point. So what is the pressure at here? We are going to search for it. So PA, here it will come minus because it is going opposite direction, upward side. Previous all the cases we are going downwards, so it was plus. Here it would be minus. So PA minus rho of oil density into G into height. How much oil height it is there? 200 mm. So 0.2. This 80 mm, there is some air. This 80 mm is air. So that is also minus rho air G into 0.08. On the other hand, you see here PB minus rho of, in this side water is there, rho water into G. Total there is water. You see 100 plus 200 plus 83, 80, 0.38. Density is given for all. So PA minus PB. So that still gives you rho oil. This two terms will come in the right hand side. So rho oil is 800. Given us 800 into 9.81 into 0.2 minus 1.16 into 9.81. Sorry, it will be plus in terms of the plus. These are the minus. So whenever we take in the right hand side, it will come as a plus. 0.08 minus 1000 into 9.81. So this way, if you calculate these things, your answer will come clearly. In terms of the kilopascal, they are asking about the in terms of the kilopascal. So kilopascal is 1000 divided. So you divide this 1000 with all the side. So this will comes in terms of the Pascal. So you have to make it. So total divided by 1000. So it will comes nearly minus 2.2 kPa, kilopascal. So you have to divide it all the term by 1000. Here already it is 1000 is there. This side also divided all the terms. And it will comes nearly 2.2 kilopascal. Concept is most important because as you going upward direction, you have to minus of it. In here also, if you go upward direction, you have to go for the minus. So that is one example here. Inverted U-tube manometer. One more simple example is here. It is the most simple thing. Example number 2 we are talking about. Here the pressure of the gas in the bulb is given. Actually, this thing we are not discussing yet. We are going to discuss this. That is about the barometer. The piezometer section, we have to discuss one thing, that is the barometer. Barometer is used to measure atmospheric pressure. Is to use to measure atmospheric pressure. It has been given by Torres. Barometer. So what is happening here? One container is there. In the container, they are full of mercury. In the container, there is a full of mercury is there, Hg. And one tube is inserted over it. One tube is inserted over it. And most important thing, the tube diameter. The diameter of this tube should be more than 1 centimeter. The diameter of the tube should be more than 1 centimeter. Why? Because to avoid capillary effect. To avoid capillary effect. If it is more than 1 centimeter, there should not be any capillary effect. It will be decreased. In such a condition, the tube is a U-tube. It's not tube is U-tube. The closed. It is a closed tube. Inside it is a fully vacuum. Inside the tube is a fully vacuum. This consideration. Inside the tube is a fully vacuum. Because of the vacuum, this mercury will goes up. Rising mercury level will rise up to a certain level. And whenever we are measuring the level of it, that is coming off 760 mm of mercury. That is the height. What is that? That is nothing but the absolute pressure of the, because here whatever the pressure is acting, that is the atmospheric pressure. Here it is the pure vacuum. Pure vacuum means absolute pressure is 0. That is a pure vacuum. So no pressure in this part. And here height is 760 mm of Hg. So P atmosphere. So here it is atmospheric pressure. Here also atmospheric, same level. So P atmosphere is equal to 760 mm of Hg. For this height. So 760 mm means 0.76 meter into 13,600 into 9.8. So this way that we have to go for the calculation, and in this calculation, whatever you are getting, that is the 1.01300 something. So 1.0 100.3 kilopascal or 1 atmosphere. That's it. So from the barometer, we are able to measure the absolute value of the atmospheric pressure. Most consideration case was it was a vacuum. This vacuum name is the Torricelli's vacuum. This vacuum is known as the Torricelli's vacuum. But actually, there is some mercury vapor will be present. Instead of getting full vacuum, there must be some mercury vacuum. In the Torricelli vacuum, there must be some mercury vapor will be present there. And because of this vapor, some vapor pressure will be there. So this value of 760, there might be some error due to cause of this vapor pressure. That is the concept in here. That is the concept in here. So some vacuum is there, but it is not fully zero. Absolute pressure, some value is there. That is the PV, the vapor pressure of mercury. Slightly mercury vapor will be present there, and this vapor pressure will be present there. This is come as an error in here. So if you write down the equation, because of this corrected equation is coming in this way, P atmospheric plus PV plus 760 into 13.6 into 3, 9. In this way, equation will be established. It is very small, though it is very small, but it has to be considered. It is termed as an error here. Now, the example 2, if you see here, example 2 is telling this bulb already having some vacuum of 50 centimeter vacuum, 50 centimeter Hg vacuum. What does it mean? It means that here already below the atmospheric pressure 50 centimeters is there. So from the atmosphere it is less than 50 centimeters there. So how much height it will be taken? So if there is nothing is there, if it is fully zero, so height will be 76 centimeter of Hg. If there is nothing is there, zero. If fully zero, height will be 76. If it is actually below the 50 centimeter of Hg, so the height will be, H will be equal to the 50 centimeter only. H should be equal to the 50 centimeter only. Because here pressure is less than 50 centimeter of Hg. So after reaching this mercury reaching 50 centimeter, it will be equalized. Both sides the pressure will be equalized. The concept, the height of the column is equal to the 50 centimeter. So how much vacuum will be here? Is a vacuum. It's telling as a vacuum, not absolute pressure. It's telling as a vacuum. Most important. Vacuum means how much less than the atmosphere. Because previous case, if you think at previously, here the pressure was zero. Absolute pressure was zero. Absolute pressure zero means how much vacuum? 76 centimeter of Hg vacuum. If it is 76 centimeter of Hg vacuum, so height will be 76. If it is 50 centimeter of Hg vacuum, height will be 50. The same thing. Because in terms of the vacuum, we are telling from the atmosphere how much it is down. So absolute pressure zero means 76 centimeter of Hg vacuum. It is. So if it is 50 centimeter of Hg vacuum, then height will be 50. Whatever the vacuum, it will be the same height it will be reached. So that is the concept in here. One interesting thing that here, multi-tube manometer, how to finding out this multi-tube manometer cases. There are so many number of tubes you could be able to say 1, 2, 3, 4, 5, 6, 7. In such cases, here, the air pressure. We are asked to finding out the air pressure. PA. Let you take PA. Air pressure you are going to find out. So what is the pressure at here? How to find it? The pressure is at here is PA plus H1 rho of air. Whatever the pressure is at here, the same pressure is at here. Same pressure. Whatever the pressure at here, the same pressure is at here. Now, what is the pressure is at here? That is this pressure minus marker it is Hg, H2 into G. There is a pressure is H2 into G. Now you see in this way, if you draw this here, also the same pressure. What is the pressure is at here? The same pressure is at this point. And that value is this one. This one is the value. Now we are interested in finding out the pressure is at here in this location. So you have to come down. So positive. So plus rho of water into H2 minus H3 into G. This is the pressure as here. Now whatever we have written, the pressure is at here. The same pressure will be found at here because that side is the same liquid. Now we are interested to finding out the interfacial here. Interface. Here the pressure is going upside. How much up? H4 minus H3. So minus rho Hg, sorry, rho Hg, H4 minus H3. That is the pressure is at here. The same pressure in the same level. So in this zone, this is the pressure. Now you are coming down at here. Interface is at here. And here, what is the pressure? The positive side it will come with the water. So rho water into H4 plus H5 into G. That is the pressure at here. The same pressure in the same level zone you are getting it. Same level zone you will getting the same pressure. Now the pressure is at here. We are interested to finding out minus rho Hg, H5 plus H6. Here, what is that? Here, nothing is the atmosphere is there. So, is equal to P atmosphere. So, you have reached to the atmosphere. In this way, you have to solve the multitude problem. So, what we are just recap, air pressure, we coming down, so plus. Next, the same pressure in this zone, here and here. Next, we go up, so minus. This term is next here and here the same level, the same pressure. Next we're coming down, we're getting the pressure here. The total pressure we get from here to here, the same pressure here and here in the same level. Now you go up, level is continuous. Your reference is changing here in the multitubes problem. After that, if you're asked to finding out PA minus P atmosphere, if you put down H1 rho A, this term actually will be cancelled out because the density of air is much less than the density of Hg and density of water. That's why this term will be very negligible. Remaining term is there. H1, H2, H3, all value is given to you. As the all value is given to you, if you put here, you will get back this equation, PA minus PB, in terms of the kilopascal, 190.31 kilopascal. But the sense is like that. First you started from here, come down, same level, go up, same level, come down again, same level, interface. You try to track the interface in this way. You're getting the answer. That is the type of the problem of the multi-tube type problems. One more type of the problem is coming here. There is a micro manometer in the differential type. It's the types of the problem. It's so many types of the problem will comes, but the separate types, 3 fluids problem will be here. Everything is same, just here also one reservoir is present. Here. Just like the previous, here also one reservoir is present. So 2 reservoir and 3 fluid system. 2 reservoir and 3 fluid system. What are the fluids are there? Consideration is the differential manometer. So one is connected with a pipe. This part is also connected with a pipe. You take here the point is 1, here the point is 2. In between P1 and P2, the pressure difference you have to listen. You don't know where it is more. So what are the fluids are there? One is the working fluids. Manometric fluid. Manometric fluid and gauge fluid. One more additional fluid is a gauge fluid. And here the consideration is the gauge fluid density is lesser than the working fluid density and manometric fluid density. Why we are using the gauge fluid? But from the gauge fluid level difference, we could be able to see the difference in the how much difference will come. As the density is the low, so very low pressure difference also, the very high scale it will come to measure, easy to measure. That is why to use the gauge fluid in addition with the other 2 fluids. So initially, if you see initial level, this is the interface between this was the interface between working fluid and gauge fluid. So this is the initial interface. After that, what is happening? Here the pressure, let you take the P, one side the pressure is more than the P2. It is your consideration. So as here the pressure is more, the height, let you take 1 and 2, height is the same. Height is, let you take is H1, and this is the initial level of manometric fluid. This is the initial interface between manometric fluid and gauge fluid. This is the initial interface between manometric fluid and gauge fluid. Whereas this is the initial interface between gauge fluid and working fluid. Gauge fluid and working fluid. There is the initial interface. Now as P1 is greater than the P2, so here the gauge fluid level will come drop. Gauge fluid levels will drop down. As the gauge fluid levels drops down, how much drops down? That is the delta H. So it is a suppressed gauge fluid. So gauge fluid here also it will come down because of the pressure difference. Here how much? Let you take. And on the other side, it is suppress the manometric fluid. Suppressing the manometric fluid. So manometric fluid height will be rise here by y by same way. by weight. So now it is the manometric fluid zone, new zone. And the gauge fluid level will be rise up to here also delta H. Delta H rise will be here. In the right hand column, delta H will be rise. Why? Because this area is the A, this area is the A. Both are the same. And this tube diameter small a, this tube diameter also the same small a. So how much rise here? Same rise will be the same for how much fall in here? The same rise will be on the opposite side, as a gauge fluid. So this is the gauge fluid. In this zone is a zone of the gauge fluid zone. Gauge fluid height is new zone of the gauge fluid. Now it is the analysis, we have to go for it. So in this zone here, it is H2 was there. H2. This is the problem, kind of the manometric problem. What is the use to take gauge fluid? Because gauge fluid will gives you better measurement. Now, what is the difference between the two gauge here? Here the difference is very small, but because of the gauge fluid, here we create the difference Y. The measurable can be Y, and your now reference axis is this is your reference axis, about which you will measure in here. About which you will measure in here. So first you write it down the continuity equation. Continuity equation is very easy. Area of the well or reservoir into how much level drops. That can be compensated by the tube area into level drops of the gauge fluid. Y weight. No doubt about it. So delta H is equal to small a by capital A into Y weight. That is here. In the same way, if you write it down the manometric equation, so P1 in the left hand side plus rho of working fluid G H1 plus delta H plus rho of gauge fluid into what is that? H2 minus delta H plus Y by 2. We come here. Similarly, from in this side, if you are coming here, how it will be? That should be equal to P2 plus rho W G H1 minus delta H plus rho G gauge fluid H2 plus delta H minus Y by 2. And remaining part rho of manometric fluid G into 1. That is the total equation. We are writing it here. PA is greater than the P2. If you write down this equation, what you are getting it, so simply here if you write it down, PA, P1 minus P2. So what would be equation you just see here? So this part is the same. Rho WGH1, rho WGH1 will be cancelled out here. Rho WGH1, rho WGH1 will be cancelled out, and it will comes in that way 2 rho WG into delta H. So we are writing it minus 2 rho WG delta H on the first term. From this two term, this and this way, this two term. From the gauge fluid, rho gauge into H2 into G. Here it will be G. So this first term will be cancelled out. Remaining part will be here. So you can write it down in this way, that rho GA again in terms of the minus rho GA y by 2 minus delta H into G into 2 from the previous one. So rho GA y by 2 minus GH delta H into G, both sides, plus rho M G Y. This will come. So hence you are getting it, rho M G Y minus rho gauge G Y. These two you separate. And remaining delta H term you are taking in a different manner. Remaining delta H term 2 rho W G delta H plus 2 rho GA G delta H. This is where you are getting it. So rho M manometric fluid minus gauge fluid difference into G into Y. And remaining part is here 2, or it is in terms of the minus also, you could be able to write it minus delta H into G, 2 delta H into G, rho W minus rho GA, gauge fluid, rho W minus rho GH. Hence, you could be able to change it by in this way. Delta H is equal to A by epsilon, Y by. If you change these values, so simply you could be able to write it down. Rho M minus rho GA into GY minus A by YG W minus rho G. This is the equation you are getting. If A is much less than capital A, P1 minus P2 can be simply you are getting from the manometric rho, manometric fluid rho minus gauge fluid rho into G into Y. This will give you the idea of it. So this way we are going to calculate for the micromanometer cases, differential micrometer cases. If it has to be significant, so this equation will get back. This equation you have to apply for it. So that's all here. We are trying to be finished. Example 3 is the last remaining portion we'll see. Here, the concept is given as the concept of the static pressure. Here it is measuring the static pressure. In here, the point is measuring the static pressure in this zone. Here, this pressure is converted into the velocity, as there is some velocity. So one pitot type tube is given here, pitot tube. And this velocity is coming here and it becomes null in this case, 0. Velocity becomes 0 here. So total dynamic head is converted into the pressure head. Total velocity head is converted into the pressure head in this case. Now in this kind of the problem, I just telling it, I try to understand. So we will apply the Bernoulli equation in here. So what is the Bernoulli equation? We will see later, but it is not beyond OPS scope. Just I am solve it along a streamline. What is the streamline? We also don't know. What is the Bernoulli equation? We also don't know. So along a streamline, here if you consider point 1, same horizontal plane you are considering here point 2. So P1, here the pressure plus some velocity is also there in this point. Before it, some velocity V. So half rho velocity square. Pressure into some velocity head. How it is coming, we'll show it later in the dynamics chapter. Just I'm writing it down, you try to follow. Here, pressure plus entire velocity converted into 0. nothing, pressure. So total, no velocity at this point 2. So total velocity plus initial velocity, this pressure is known as the static pressure. Static pressure. And this is the dynamic pressure. The static plus dynamic here, whatever the pressure we are getting, this pressure name is stagnation pressure. Because we make the fluid that is stagnant in here. Velocity becomes totally zero in this point. The point, it is the condition of the adiabatic condition. Will comes in the whenever we are analyzing the pitot tube, the total pressure definition, stagnation pressure or total pressure definition, total temperature definition will comes all the things. Just it's a scope this kind of the, because it's not a manometric problem at all, but still here given, so I'm just analyzing the total head because of the pressure and because of the velocity. This two head, energy per unit mass, is converted into the total pressure or stagnation pressure. So this difference P2 minus P1 is nothing but half rho square. What is rho? Rho is the gas density. It's given. Rho is the gas density. So rho is given as the 1 kg per meter cube. This pressure difference is nothing but is equal to half rho v square. That has been measured by this manometer. That has been measured here. So in this case, if you consider from here to here, you have to draw one reference line here. The reference line x dash and point 1. So point, this is the both 1 and 2 point are at horizontal point, and it is the height is latitude z. It is same point. So P1 plus rho gz. Rho gz is there. P1 plus rho gz minus h. Plus, here manometric fluid is taken as a water. So rho water G into H. That is the pressure at this point. What is the pressure at here? Here the pressure is the P2 plus rho gz. P2 plus rho gz. So P2 minus P1 from the manometric equation, rho gz will be cancelled out from the both sides because z is just a variable term we are taking arbitrary. So it will gives you that rho w minus rho g into h. So rho w is 1000, rho into is 1 into 9.81 into h is given as h you have to ask to find out. What is the h you have to find? P2 minus P1 is nothing but half into 1 into velocity is given as a 20 square. So velocity given as a 20 square. So that is the 200 divided by 999 into 9.8. That will come as the h. This will comes as the h. So h will comes nearly 20 mm. So h, if you getting the h value will comes nearly 20 mm. Very close to the 20 mm. 20.4 mm is the answer. H value you're asked to finding out in mm, so it will comes nearly 20.4. The concept is like that. The total pressure is converted as actually static pressure plus dynamic pressure is converted into the stagnation pressure because of this period tube type arrangement. And that's why we are getting whatever the velocity head or dynamic head we are getting, this dynamic head is shown in the manometer. That is the type of the problem. So here we are concluding this fluid static portion. There are no more other than one portion is the rigid body motion of the fluid under the rigid body motion. That's some tanker. It is not under the fluid statics. We'll discuss this topic in the later. Some more points of the question is here asked. You can go through it. I will just giving some answer also. Here is given the what is the center of pressure or pressure center. So answer is actually the cycloid of the pressure prism is showing a point on the line of action of the resultant force at the centroid of the submerged area and always above at the centroid area. These are all other things is telling you. So hence here the answer is the P. Because center of pressure is such a point over which the resultant force is acting. The line of resultant force is acting over this point. So B is the answer other than all. Next is asking the vertical component of the hydrostatic force on the submerged curved surfaces. That's we already discussed. That is the weight of the liquid vertically above it. So it's the liquid, weight of the liquid vertically above it up to the free surface. Above it up to free surface. That has to be also mentioned. So up to free surface, the weight of the liquid, it should be here. Next question is given as a tank with 4 equal vertical faces of width is given. L and depth is H is filled up with the fluid. If force on a vertical side is equal to the force at the bottom, then what should be the value of H by L? This problem you try it, it is not more difficult problem because a tank is the vertical shape is given 4 equal vertical faces there. So over the vertical side, what is the force is acting? So over the vertical side, the force is acting as the horizontal force. And the force at the bottom, it is acting the hydrostatic force because of it. Both are equal. If both are equal, so what should be the H by L? It is such an easy problem. If you go for the what is the forces over the vertical surface is acting, you just if you write it down, the force formula over the vertical surface, that is the rho G HC into A. So how much depth it is? The depth it is here. Depth is H by 2 because it is filled up to H by 2. And what is the area of this vertical surface? That is H into L. This much area. This much force is acting over it, over this vertical forces. On the other side, at the bottom face, it is acting at rho G into H. In the bottom face, it is acting rho G into H into L square. Into L square. Because the vertical side, equal vertices face is the L, which is the L. So that is the force is acting on it. So if you do it, so H by L, you were asked to finding out. So rho G will be cancelled out from here. 1H will also be cancelled out. L will also be cancelled out. So H by L will comes as a 2. So the answer will comes as a 2 in this way. You try this problem. It's an easy problem, not that much difficult. Which one of the following is the condition for stable equilibrium for a floating body? This is the question for the fluid statics, the IS 2005. This kind of question is frequently asking. It's a very easy to answer. For the case of the floating body, which is deciding factor is the metacenter position. If the metacenter is above the center of gravity, stable equilibrium will be always in terms. In this case, if metacenter is below the center of gravity, unstable equilibrium. We have already discussed last classes. If metacenter coincide with the center of gravity, neutral equilibrium. Center of buoyancy having no role with the center of gravity. This role is coming whenever it is submerged body. The submerged body. So this no role of it. Next is the metacentric height of the passenger seat is kept lower than that of the navel or cargo seat, because what is the reason of it? This question we have already discussed last thing, because you see the omega natural frequency is coming in terms of root over of GA, metacentric height. So if you increase the metacentric height, the frequency, if you increase the metacentric height, natural frequency is increasing for the cases. So this is causing for the, if you go for the GM high, your natural frequency will be also high. That's what gives you discomfort for the passenger. So for the sake of the comfortness, we try to GM some least value, optimum value. Don't go beyond of this optimum value. So in that case, the passenger seat is keeping low of GM. Because if you keep low, so your frequency of rolling will be decreased. So it will not give further discomfort for the passenger. This way we are getting this problem. Next thing is the depth of the center of pressure for the rectangular lamina, which is immersed in the water up to height h is given by. This is also easy question, you can able to get it, because a rectangular lamina, it is immersed up to h, height is h. Where is the depth? The height is the h. One rectangular lamina is okay. The depth of the center of pressure is asking. So centroid is at h by 2, no doubt about it. It is immersed, height h, so centroid is at h by 2. H by 2 is the centroid. Now you're asking the depth of the center of pressure. Center of pressure depth, how to get it? If you remember this thing is equal to the formula, the center of, whether the depth of the center of pressure, HP is equal to h by 2 plus of IG divided by A, HC, that is meant by h by 2. So what is the IG here? If you other dimension, if you take it as a L, something else, it will be cancelled out. L into H cube, L into H cube by 12. What is the area? Area is the H into L into H by 2. This way. So L will be cancelled out. You can see it. H is also cancelled out. So H by 2 plus H by 6. It gives you the HP times. So hence 4H by 6. So 2H by 3 will be answer for this question. This way you have to practice this kind of a question. Because this formula, to remember this formula is not easy. It's not that much difficult for things. One formula, if you remember, if you forget, you're getting time, you will go for the derivation. Derivation is very easy for this. Next is the match list is given to you. The match list. Unstable equilibrium. We know this unstable equilibrium is for the metacenter. It depends on the metacenter for the floating body. So for the floating body metacenter, so M is below the G. For the unstable, A for 3. Neutral equilibrium, mg is equal to 0. B is equal to 1. And stable equilibrium is M is above the G. So 3, 1, 2 is the answer. Very easily you can get it. If you go through the portion, it can be getting it very easy. Here the question is slightly tricky in that case. The vertical clean glass tube of uniform bore is given as the piezometer. We are going to use it as a piezometer. The liquid having the specific weight is given as 15 kilonewton per meter cube. Specific weight means rho into G. Specific weight means not only rho into G. Rho into G means specific gravity into G. So specific is divided by rho water. It's a rho by rho water. Specific gravity into G. In this term, it is used. So the liquid has the specific weight and surface tension is also given to you. Here, the surface tension is also given to you. 0.6 Newton per meter in contact with the air. So angle of contact with the gas is given 0. Capillary rise should not be exceed more than 2 mm. This 2 mm error we can withstand. So what is the minimum diameter you require for this? This is called the IS question. So they merge it in it's a surface tension problem. Looks like a piezometric problem. So this kind of the problem, every data is given. If you go for the surface tension problem, the capillary height, if you remember the capillary height formula, otherwise you can solve it. It is not a big deal. 4 sigma cos theta rho g d. You can remember it or you can solve it. Solving is also very easy for this case. Whoever not remember, they can solve it by in this way. One capillary tube we will take. And here the height, surface tension sigma is acting. So because of the sigma, what is acting? Sigma into pi d force, upward force is acting. Sigma pi d into pi d is the circular portion into cos angle. This is acting. This is the force is upwards. This upward force is able to hold this height. This much water column height. And what is that? Water column height is pi by 4 d square. Height into rho. This weight, it can withstand this weight. From this formula, you are getting it. So pi will be cancelled out, d will be cancelled out. So 4 sigma cos theta divided by rho gt. This formula. So H, so capillary height should not be more than 2 mm. 2 mm. So 4 into 0.06. Cos theta is already 1 because cos 0. Rho g is given as the 15 kilonewton per meter cube. 15 kilonewton per meter cube. Rho g is given as this. And d, diameter, what is the minimum diameter? They're asking for it. So d is asking. So 15 kilonewton per meter cube is the rho g is given here. Because if you go for the kg into centigrade, kg centimeter per in this one. So rho g is given as a 15 kilonewton, 15,000 Newton per meter cube in this way. So d will get you in this manner 4 into 0.06 divided by 15. So d you can able to finding out in this way. So here, your answer will come nearly 8 mm, I think so. It should not be more than this, 8 mm or 12 mm. Okay. So you, just for the calculation, in the sake of the calculation, it's not more a big deal, you can do it. That's all. Next is the when can a piezometer not used for the pressure management, pressure measurement in the pipe. We have seen it. The piezometer cannot be used when there is a fluid is in the pipe is a gas. We should not use piezometer because gas cannot gives the level. Pressure difference is low, can be handled. Velocity is high, also can be handled. Pipe is highly viscous, also can be handled. So answer is a C. Question number 10. You search for it. You try it this way. A free falling of the influence of the gravity. Free falling is going on. So a surface beaker, it is free falling. Free surface it is. Free surface, one point is there, B, and here one point is C. So what is the pressure? B and C. My concern is the pressure will be equal because no relative body force in the direction because it is as it is free falling. So you try for it. What would be the answer in this question? So this all hopefully complete here. You try this, any error, you will tell me. I'll rectify this problem. Okay, thanks for today. Fluid static is complete over here. Next day we'll see the kinematics of the fluid, and after kinematics, dynamics of the fluid. That time we will see the rigid body motion, the fluid under rigid body motion portion also. So we are completing here over the fluid statics portion.